What's up, y'all? I'm Tom. This is Like a Math Class. In this video, we're going to talk about the basic rules of anti-differentiation. But before we get to that, let's break down some of our notation so we actually understand what we're talking about. Let's get to it. All right, so to begin with, anti-differentiation is also known as indefinite integration. We call it indefinite integration because, the antiderivative itself is called an integral, but it's indefinite because we're not putting specific boundaries on this integration yet. We're going to put boundaries on it later, but right now we're just finding the integral or the antiderivative of any given function. So what we're used to is we've started with this idea of dy of dx is equal to some function. Now we often write this as the f prime of x, but we know that f prime of x can be a function in and of itself. So I'm just going to call it f of x for the purposes of kind of laying out what it is that we're actually talking about. If we want to kind of consider the notation that we're going to use, the first thing that I want to do is I want to move this dx over here. Now you can't really move d of x from one side of the equation to another, but we sometimes do that just to kind of get a feel for how we can rearrange these things and kind of keep track of everything in our head. So we're not really moving it from one side of the equation to the other, but we're kind of doing that just for our own notation purposes. So that leaves us with dy is equal to f of x dx. And that's telling us still that we've got the derivative of y is equal to something, but what we want to do is we want to figure out how do we get to y itself. And what we're going to do is we're going to take the integral, we're going to use this kind of funny squiggle symbol, that's the integral symbol, and we're going to take the integral of f of x with respect to x. And now in some books you might see the notation as capital F of x plus c, and this is just another way to indicate that this function is different than this function, so we use a capital F as opposed to a little f. But that's just going to be based on where you're at within the problem and what type of work that you're doing. So what does all of this mean? So first off, this is what we're considering our new function. This thing here, the f of x, this is called our integrand. This dx, this is the variable of integration. And what the variable of integration means is it's just like when we're taking the derivative of y with respect to x. So y is by itself, and then we do all the derivatives with our x. This is telling us when we're integrating all this stuff, when we're moving back to our original function or the integrated function, we're doing all the integrals on that variable. In this case, it will be the variable x. And then finally, this plus c, this is called the constant of integration. It's the constant of integration because, as we saw in our last video, which you could also see right here if you missed our last video, anytime we take the integral of a function, there may have been some constant at the end of that, so we need to always include some stand-in value, some stand-in variable, c, that we'll put in there in case there is some constant that we have to put in there. And we find that through various bits of information given within a problem. So what all that breaks down to is our integral of f of x with respect to x, that's how we say that, is actually the antiderivative of f of x with respect to x. So you may have even noticed I said basically all of this when I wrote this. The integral of f of x with respect to x, the antiderivative of f of x with respect to x. So that's how you read that, that's how you say that, that's how you use that language when you're talking about these different types of functions. So now let's focus on some of our basic rules. The first one that we've already talked about in our previous video is called the power rule. And that says if your function that you're integrating is x to the nth power, then the integral of that function is going to be 1 over n plus 1 times x to the n plus 1 power. What an actual example of that might look like, let's take the integral of x to the 6th with respect to x. So that means n is 6, so I'm going to have 1 over 6 plus 1 times x to the 6 plus 1 plus c. And then as I simplify that, it's easy enough, 1 over 7 x to the 7th plus c. That would be the integral of that first value, just using the straightforward power rule. Then we have what I call the constant multiplier rule. The constant multiplier rule says if your function has a constant times another function, then the integral of that original function. So here again, we're looking at the function, the integral of that function is going to be equal to a constant times whatever that other function was inside there. So what does that look like in actuality? So if I'm looking at the integral of 3x to the 5th power with respect to x. Okay, so now here I've got 3 times x to the 5th. X to the 5th, I would just be using this power rule over here. This x to the 5th is the same thing as this g of x here. So I've got 3 times this other function. So then my integral of f of x, this whole thing, is going to be equal to the constant 3 times the integral of x to the 5th with respect to x. That's what's happening right here. The constant times the integral of the other function, So I'm going to carry down my 3. The integral of x to the 5th we've seen is 1 over 5 plus 1 x to the 5 plus 1 plus c, which then simplifies to 3 over 6 x to the 6th plus c, or 1/2 x to the 6th power plus c. And this again I call the constant multiplier rule. And hey, let's give the power rule its own little box here too. I mean, you want to pay respect to the power rule, because after all, you're going to be using that one a lot. Our next rule we have is called the constant rule. The constant rule is saying if your function is just a constant value, just a number, then the integral of that function is a constant times x, or whatever variable you are integrating with respect to. So let's say we've got the integral of 4 dt. Now I'm going to use a different variable here so we can see that it's not always going to be x. But the integral of 4 with respect to t, okay, so now it says my variable of integration is going to be t. So that means the integral of this thing is going to be 4 times, well, whatever variable I had. But now I'm using t, so it's just going to be 4 times t. And of course, we're going to add a plus c on there. Of course, and usually we don't put that times in there, so we'll just say 4t plus c. And again, this is what I call the constant rule. And now we've got one more that to kind of round us out for the basic rules, and that's called the sum and difference rule. So here, if our function is the sum or difference of two separate functions, then the integral of the whole function is equal to the integral of the first piece plus or minus whatever the case was up here, the integral of the second piece. So let's say we've got the integral of x plus the cubed root of x with respect to x. So now if I want to integrate these two things with respect to x, this would be like my g of x. This here is similar to this, and this here is like this piece right here. So we're taking the sum of these two separate functions. So what I want to do then is I want to take the integral of x with respect to x, and I'm going to add, because I'm adding right here, the integral of the cubed root of x, which is x to the 1/3 with respect to x. All right, that should be easy enough. The integral of x, that's x to the first power, so 1 over n plus 1. So that's going to be 1 over 1 plus 1, x to the 1 plus 1, plus 1 over 1/3 plus 1, x to the 1/3 plus 1. And then we're going to put a big plus c on the end here. And let's give ourselves a little space here so we're not so squished with our plus c. They've got to have their space too. All right, so we're going to have 1/2 x squared plus 1 over 4/3 x to the 4/3 power plus c. So we're going to simplify that, and we're going to have 1/2 x squared plus 3/4 x to the 4/3 power plus c. And that is a nice demonstration of our sum and difference rule. So you're just taking the integral of each individual piece. Now, if you've been paying close attention, you might have noticed all of these things follow almost the identical basic rules of differentiation. Duh, of course they do. Differentiation and integration are two sides of the same coin. You've got a function, you take the derivative of that, You take the integral of that and you get back to the original function. They get you, that's just moving back and forth. So of course we're going to have similar rules that follow along with these. If you figured that out yourself, give yourself a thumbs up. And hey, while you're at it, give me a thumbs up too and like the video. Now I've got one more example that I want you to look at, and it's a question that you're often given as you're learning integration, and I don't want you to get tripped up with something like this. And that is, find the antiderivative or the integral of g of t when that equals t plus 1 times t minus 3. Now what we haven't learned is how do we find the integral when we're multiplying two things together. We've learned about the power rule, the constant multiplier rule, and the sum and difference rule, but no product rule. So what do? Well, we do probably exactly what you're thinking we do. We're going to take g of t before we integrate it, and we're just going to expand it to t squared minus 3t plus t minus 3, which is t squared minus 2t minus 3. There's our g of t, and now we're going to integrate g of t. So we'll find the integral of g of t with respect to t, because that's our variable of integration. And I could also write that as the integral of t squared minus 2t minus 3 with respect to t. But any way I write it, I'm going to ultimately end up with the integral of t squared with respect to t minus the integral of 2t with respect to t minus the integral of 3 with respect to t. So now we get to use all the different rules that we've been working on in this whole video. So the integral of t squared, 1 over 2 plus 1 times t to the 2 plus 1 power, minus what we said we're going to take 2 times the integral of t. This is t to the first power, so it's going to be 2 times 1 over 1 plus 1 t to the 1 plus 1 power, minus 3. Now the integral of 3 of a constant we said was just going to be 3t, and then we're going to add c to the end of all of this. We don't have to do c to each one of these things because this whole thing is one function, so we're just going to have that one constant of variation on there. And now let's simplify, where we've got 1/3 t cubed. Let's see, minus 2 times 1/2, that's going to be minus t squared minus 3t plus c. Now, as I mentioned, I always like to check my work by doing a quick derivative, so let's do that just to make sure that we did all of our integration right. After all, this is the first time we're doing integration, right? So here's our check. 3 goes out here, so we're going to have 3 times 1/3, which is 1t, 3 to the minus 1 power, that's going to be t squared. Okay, check. And then we're going to have minus t squared. So minus t squared, let's see, the 2 comes out here, so we're going to have minus 2. T goes down by 1 power, t to the first power. Hey, minus 2t to the first power, so check. And then minus 3t, well, when we take the derivative of a constant times t to the first power, that's just going to be minus 3. So minus 3, check, and we are good. So indeed, this is our integral of our function. There is our solution. So we're going to get into more rules of anti-differentiation, more rules of integration, but this should get you started with the foundational level, the basic rules that you need to know inside and out.